Well, thank you very much for that kind introduction. It is very good to be back in Memphis, and a special treat and honor to be the first Donaldson lecturer here as part of this series. I should thank Joanne Rhodes as well, because she's really the one who's brought me back and reminded me of the wonderful time that I had here, what would be 37 years ago, when I was just starting out my career. Because the meeting at that time in 1979 was really an event here on the campus. I think it was Memphis State University then, wasn't it? And it was an international gathering. And it coincided, the talk I was giving that day, with the announcement that was being made in Cambridge of a major discovery that my group had made concerning the black hole, supermassive black hole at the center of the Milky Way. And so it was an event for me on this campus because I remember I had a New York Times reporter traveling with me wherever I went on campus that day. There were numerous impromptu news conferences occurring all through the day, and calls were coming in from all over the world. Of course, by contrast, my scientific colleagues were very skeptical of the work we had done, and were not yet buying into the notion that the center of our galaxy was inhabited by a supermassive black hole. Alas, 35, 37 years later now, every leading textbook routinely states that there is unquestionably a supermassive black hole. So that's how science works, of course. When you're doing it in the trenches, the fog of war, it's always very confusing. But eventually the data come in, the evidence is accumulated, or doesn't, and there are winners and losers. In this case, we were a winner. But I really do remember that visit to Memphis previously. In fact, of all the, something like well more than 1,000 college campus visits I've made in my career, that one in Memphis stands out as one of the really exciting ones. And I'm sure today will be as well. But of course, that kind of work that I was doing then, and I still do now, is work that I do with my right hand. That's specialized work. That's the stuff that's done, the real solid science that gets written up for the indecipherable journals that hardly anybody reads. Well, no, I shouldn't have said that perhaps, but I want to share with you today not necessarily the work that I do with my right hand, the highly specialized work, which is my day job, but rather the work that I do with my left hand. That's the work I do that I really love, I have a passion about, that I do in the, the evenings, the trains, planes, weekends, holidays, when I can sneak a little bit of time. Because for my entire career, I've been trying to, from a scientific point of view, understand who I am. It seems kind of odd. Where I've come from. And really, scientifically, how do I, as a human being, and all of you as well, life in particular on this planet, fit into the larger scheme of things? Of course, I realize full well at the outset of this talk this evening that many other endeavors attempt to do this as well. There's art, there's literature, there's music, there's poetry, there's philosophy, there's religion, and there's science, among other endeavors that all attempt to say something about who we are and how we fit into the larger scheme of things. But I'm a scientist, that's my calling. So I bring to bear on these subject matter data, evidence. I'm always saying to my students, show me the data, I'm an empirical materialist. I confess that up front. Not a dialectical materialist, as I told them recently in Moscow, but an empirical materialist. I always want to see the data, and I want to try to test ideas. I'm obsessed with testing the universe and all of its contents, observationally and experimentally. Largely because I want to use the test as a means to discriminate between what is sense and what is nonsense, and get rid of the nonsense as quickly as possible. And thereby accumulating a certain amount of the sense, I can gain, not the truth, I wouldn't know what the truth is, I wouldn't know how to define it, but I can gain, by accumulating sense, a better and better approximation of reality. So I am a scientist. In particular, I'm an astrophysicist, which means I'm trained in physics, and that I've adopted the universe as my lab, the whole universe. I want to suggest to you that this is a very exciting time to be an astrophysicist. I want to suggest to you that when historians of the future, 500, 600, 700 years in the future, write history books about us, they're likely to conclude that we are now living in a golden age of astrophysics. And the reason I say that is that we are opening up in a single generation, not the generation of my children, not the generation of my parents, but our generation now, scientists in the trenches working on science. We're opening up the entire electromagnetic spectrum and seeing the universe and perceiving the universe in all of its variable wavelengths. And we're doing, To quote Galileo, who opened up the visible universe one night in January of 1609, we're seeing the entire universe and all of its wondrous contents in a variety of magnificent ways. And the advancement of astrophysics and the number and diversity of discoveries right now in the early part of the 21st, it's astronomical, really. Bad pun. But by the same token, I want to suggest to you that our kids, those are all apostrophe S's, are probably grandchildren are likely to write books about us that also say that we are now living today in the golden age of biochemistry. Because I think in many ways the advances in the biomedical community are equally as outstanding, equally as magnificent, equally as astounding and awesome as those being made in astrophysics. I find myself increasingly at MGH, Mass General, and Harvard Medical School at their invitation because of their having interest in some of the things that I do in physics. Very interesting relationship. In fact, I've found that the work in biomedical community and biochemistry in particular is so outstanding that I have to confess to you, I wish I had been a biochemist. But by the same token, I was at dinner the other night at MIT with a biologist sitting beside me who happened to be a Nobel laureate. And after a certain amount of lubrication, he confessed to me that he wished he had been an astrophysicist. So maybe the grass is always greener in the other yard. But I mentioned these two subjects, these two interdisciplinary subjects, astrophysics and biochemistry, because in my career I've had the opportunity to work in each of these, to research in each of these areas, to publish a little bit in some of them, and to understand some of the wondrous discoveries that are being made in our lifetime. But furthermore and more fundamentally, I've been trying to, with my left hand, after hours, for 30 years or more, understand whether or not we might be able to synthesize these two already interdisciplines into a grander interdiscipline, a transdiscipline, if you will, and that is what I call cosmic evolution. Now, if you ask me, what do you mean by cosmic evolution? Define cosmic evolution. I would simply say immediately, it's just a study of change. And if you put me into the corner, put the bright lights on me and say, what do you really mean? I would say it's something like, I'm making it up because nobody's defined it before, right? It's something like the study of the endless changes, developmental changes, evolutionary changes among all matter, all radiation, and all life throughout the history of the universe. It's everything. But that's the essence of not necessarily in this talk stressing the work that I do with my right hand. That's the specialized work I do every day in the trench. That's the work I do as a splitter, a highly specialized researcher. In this talk, stressing the work I do with my left hand, I'm a lumper. I'm trying to lump these subjects together. I'm trying to explore whether there's unification in the sciences and beyond. I'm interested in the bigger picture. But I'm selfishly interested because I want to know how I fit into this picture before I leave the planet. I want to really know where I've come from a scientific point of view, recognizing and respecting that there are other points of view and other endeavors that are also trying to do the same thing. But I've bought into this notion of the scientific method that requires me to test ideas, test beliefs. We claim, back in Cambridge, that neither thinking alone nor believing alone will ever make the unknown known. You've got to test an idea. You've got to observe. You've got to go experiment. You've got to be skeptical. You've got to say always, show me, show me. That's just the calling I have. That's the bias I have, and I want you to understand that up front. But I do respect others who have a different bias. So I mentioned these two subjects, astrophysics and biochemistry, to emphasize the notion that I'm interested in change. And I realize where I am in Tennessee. I recognize that some people here and elsewhere through the country, if not the world, get hot, bothered, sticky, and upset at mention of the word evolution. But I can assure you that the word evolution, it's not a dirty word. It implies neither dogmatism nor atheism. It's just hardly more than a fancy word for change. And when I look out the window, you know, my philosophical window, and I see out the window galaxies, stars, planets, life, society, machines, etc., all these complex systems, I I defy you to show me some of those, any of those systems that aren't changing, provided you look long enough. Some of the change that I see out the window is subtle. Other of the change is very dramatic. It's subtle in the case of, like, the sun comes up every day, or appears to come up every day. It doesn't seem to be changing very much. But over the course of time, there's very definite changes that we can detect. And in other stars, more massive than the sun, they change dramatically in a supernova, blow themselves to smithereens, and then there's really dramatic change. Or similarly on the surface of the Earth, where the plates are moving very, very slowly on the surface, at the rate at which your fingernails are growing. Hardly any change is perceived. We live on these plates. But over the course of time, of course, eventually some of those plates dislodge and slip, and enough to cause an earthquake or a volcano, enough to lead the evening news. Some of the change is subtle, some of the change is dramatic. But again, what I see out the window in terms of a common denominator, a unifying precept, perhaps, is change. Change writ large. So I give this universal change the fancier name, cosmic evolution. That's all. Two caveats. One, when I say this evening, cosmic evolution, I'm not just talking about astronomical systems. I'm talking about all such complex systems, whether they be galaxies, stars, planets, life, society, etc. Big and small, near and far, past and future. Second caveat, when I talk about cosmic evolution, I'm not trying to take the essence of neo-Darwinism or the kind of biological evolution that's controversial in some areas and extrapolate it on into the universe. I'm trying to do more than that. Sounds arrogant, but that's my agenda. I'm trying to explore whether or not there is an underlying theme, a process, a mechanism, a principle, maybe even a law of science that will enable me to understand how it is that all complex systems have come to be in the same common denominator, in the same common mechanism. I'm a unifier. I'm a lumper, not a splitter tonight. When I go back to Cambridge tomorrow, I'll be a splitter again. So what I'm trying to do really with cosmic evolution is to create a cosmology in which life plays a role. It's a cosmology, a worldview, in which we all have a position to play, maybe a role to play. It's a cosmology in which life is evident. It's a cosmology, as a student told me last night around midnight. I was still teaching last night at midnight at the Harvard Observatory, so it's been a very long day. I'm not even sure where I am, no. He said, what you're trying to do is you're trying to create a philosophy, a new philosophy. I said, well, okay, as long as you say it's a scientific philosophy. Because I'm trying to address some of the fundamental questions that have always been addressed by philosophers and theologians and other great thinkers. But now I'm trying to, and others who work with me, are trying to bring to bear on these questions the power, and it is a power, of science and technology by demanding, again, tests, demanding collection of data in the spirit of an empirical materialist. So what are some of the questions, in addition to the ones I've already mentioned? Who am I? Where did I come from? How do I fit into the larger scheme of things? One of the central questions I want to drive at tonight is the idea that as you look out the window, you see a fair amount of complexity. I'll define complexity a little later. I could do it for you now, but you'll see it in writing in a minute. It might make more sense. But you know, and by complexity I mean these systems, galaxies, stars, planets, life forms, you and I, society, machines. These are all complex systems at some degree of complexity or another. And yet, if you ask a physicist, what is the most cherished law in all of physics? She would say, it's the second law of thermodynamics. The second law of thermodynamics is the entropy law. The entropy law is the law that suggests that things ought to, if left alone, prima facie, break down, move toward simplicity. So we have an interesting reconciliation in front of us that needs to be made. How can we reconcile the evident constructiveness that I see out the window with the most cherished law in all of physics, which suggests just the opposite ought to be occurring? Then, to make a long story short, and to give you the one-sentence synopsis of an entire course, is that these systems of varying degree of complexity are embedded in an environment. And the systems per se can develop a certain amount of complexity while they, to use a technical term, lower their entropy. But in the environment around the systems, the entropy still rises, such that if you consider the environment and the system together, the second law of thermodynamics, that cherished law in all of physics, the last one we want to hold on to when all the other laws of physics have failed us, is still obeyed. I believe, I shouldn't use that word, I reason tonight that all of what I tell you about, that I've learned in 30 years about complex systems, is in accord with the second law of thermodynamics. I'm not trying to create new physics here. In fact, I don't think anything that I say tonight will require any new kind of science. It's just a synthesis of science that many, many people are doing that I'm trying to bring together, and others as well through my work. So this is my archetypical graphic, the arrow of time. And immediately you can stop me and say, well, what do you mean about time? Define that. Well, we could be here for a while. I mean, 5th century St. Augustine, he said time is pretty obvious until you try to define it. Psychologists tell us that time is a way of distinguishing between the past and the future by way of the present. Einstein taught us that time is the 4th dimension. I kind of like Henry David Thoreau's view of time. Time is a stream that I go fishing in. That's my, I live across the street from Thoreau's house in Concord. But the arrow of time is a way to encapsulate in a single page the entire scenario of cosmic evolution as I see it in my head, running time from left to right, with a Big Bang, or the origin of the universe, on the left, and the present time on the right. And I see, by looking out into the universe, out my window, and on the Earth as well, of course, I see a wide variety of epochs. In fact, about 7 of them, interestingly enough, and an 8th for the future. And these epochs capture the sequence in which systems have become increasingly complex, have emerged, originated, and have begun to change over the course of time. There's a particulate epoch in the early universe when there were only particles of an elementary nature. Somehow those particles became atoms that eventually became the galaxies. Somehow those galaxies spawned the stars. Somehow the stars were formed with planets. The planets in turn enabled environments to allow the chemical building blocks of life. The chemical building blocks of life somehow became life. Life became cultured in the technological society in which we live. There's this thread of change running across this entire arrow of time. A thread of change that suggests that the universe in bulk, at least the systems that we identify within the universe today, have moved from one of simplicity to increasingly complex systems. One of inorganic materials to organic. One of the old-fashioned chaos in the Greek sense to one of order. I'm interested in understanding how this order and complexity arose and how it's changed. And in particular, how it has increased over the course of time, despite the second law of thermodynamics. There's a lot of information in this slide. This is the opening slide of a course that I teach at the Harvard Observatory. And you can just Google Cosmic Evolution Harvard or Cosmic Evolution my name. This will come up as the top Google choice. And it's free. It's open access. You don't have to pay a dime. And it's the essence of the course. It's a very, very heavy-duty multimedia site, millions of words probably by now, lots and lots of illustrations. All these are hot items, HTML hot. There's a variety of movies that we've made for this site. There's not only an introductory track that would be suitable perhaps for non-scientists, as are many of my students at Harvard in the course I currently teach. But there's also an advanced track embedded within this. It runs parallel that would be more suitable for upper level physics majors or graduate students in the sciences. So it's all free. You can access it, and if you want to just come along with us in your own way, you can access the entire syllabus that I use and see exactly how we do this. It's all free and open access. So we live in this Big Bang cosmology. And there's basically 3 major pillars for the Big Bang cosmology that we've identified in the last half of the 20th century, really. One of which is shown here in this Hubble Deep View namely the recession of the galaxies. It's a Hubble deep view, and on top of the deep view from the Hubble telescope in orbit is a variety of numbers, and those numbers are measurements of the spectroscopic scans of each one of these many galaxies contained in this view here, as seen not by Hubble but by the Keck telescope on Mauna Kea, Hawaii. Hubble takes the picture, Keck does the spectroscopy. It's an interesting picture because it's even alone, it's the deepest, most sensitive photograph ever taken by humans. It's about a 110-hour orbit, 110-hour integration or exposure in orbit from the Hubble telescope. So it enables you to see very, very deeply. It resulted from Al Gore repeatedly asking me when he was still a senator, what will Hubble's greatest discoveries be? And I kept telling him we don't know. By definition, if I could tell you what the discovery was ahead of time, it wouldn't be a discovery. So when he asked me that the fourth time, we decided with NASA, with the head of NASA, that we would take Hubble and just point it into an area of the sky where we had seen previously nothing, just blank nothingness. And out of that blank nothingness came this view here, this Hubble Deep Field that contains about 4,000 individual galaxies, each one of which, of course, contains about 100 billion stars. But the point I'm making here, without going into a lot of the details of the galaxy issues, is that all of these galaxies seem to be receding away, and they play in very strongly now to the notion that the universe is expanding. Not that we're at the center of the universe. There is no center. There is no edge. Everybody in the universe, if there are other bodies out there, would have the same kind of expanding view of the universe, the view of the expanding universe. And it leads to the notion that once upon a time long ago, about 14-ish billion years ago, the universe was a whole lot different. It was hotter, denser, and less complex. In fact, very simple. There's another piece of data. I'm just adjusting this. Uh-oh. Not to worry. We are? There's another piece of data, the second pillar of Big Bang cosmology does not come to us as from matter here, but from radiation. This is an oval projection of the oldest fossil. It's a fossilized radiation that has come to us from the early universe, as measured in this particular case by European satellite in orbit. And it also is in agreement with the notion that's derived from this photograph here of the recession of the galaxies, that yes, there was a time in the early universe when the universe was younger, hotter, denser, and much more simple. Out of that simplicity arose eventually, somehow, some way, complexity. There's a third pillar. I'm going to put it aside unless people want to interrogate me about it later. It's a little bit more complicated, and it concerns the super lightweight elements in the early universe. But I do want to get a little bit more technical right now for a few of the physicists in the room and others who will be able to understand the next slide. But the next slide is going to take these data and graph it. And it's going to graph the two most important quantities, in my opinion, over the entire history of the universe. I tell my kids, my students, that if you're in the backyard and you pick up something in the backyard, you can't quite understand what it is. You should immediately try to get its density and its temperature. If you can, as a thermodynamicist, understand the density and temperature of something, you can understand a lot about that alien piece of matter. So what I'm going to do in the next slide is to take these data here and present for you the run of density and temperature throughout the entire universe. It doesn't present the density and temperature of any rock or any substance or anything, system or otherwise in particular. It just shows the run of density and temperature generally for the entire universe. It's a lot of technical detail. In fact, back in Cambridge, I would spend about 53 minutes actually. It's a microcentury, by the way. 53 minutes just talking about this slide and all the implications that go into making the slide and interpreting the slide, the assumptions. A lot of assumptions go in. That's the beauty of teaching sharp kids. They constantly intellectually attacking me, constantly asking about the assumptions and always revisiting the assumptions every year. It makes the subject so much more powerful and enriched. But I'm running here a vertically enormous range here as a function of time. I've got the time scale plotted irregularly here. It's called the logarithmic scale, not to worry about it. But it just shows, this graph does, an important message that's gleaned from these data that I showed you previously, data that are material data and data that was previously up in the oval of a radiative nature. And it shows the temperature coming down. And it shows the density, rho, coming down. That is to say, in the early universe, toward the beginning of time, the universe was, as I said, very hot and very dense. And then over the course of time, because the universe has expanded, the density has diminished, and the temperature has diminished. Today, about 14 billion years after the bang, the temperature is very low, and the density even lower. We'll come back to some of these issues, but you see the run of the curves there. The run of the curves is such that in the earlier universe, when the density and temperature was very high, we call that the radiative era, or the radiation era. There could have been no complexity. Everything that reigned in the earlier universe, I'm talking about in the first few years of the universe, had to be of a simple nature. If something as simple as an electron tried to come together with something as simple as a proton to make what? Hydrogen. The radiation was so seriously severe, the radiation would blow that atom apart. There could not have even been atoms of hydrogen, the simplest atom in the earlier universe, let alone galaxies, stars, planets, or people. But eventually, and only it seems because the universe is expanding, as the density and temperature came down, systems were able to begin to emerge of a complex nature eventually over the course of time. So in contrast to these curves that are coming down over the course of time in an expanding universe, we have this gut feeling. It's another graph, but it's just heuristically presented here. Again, the same logarithmic view of time, from the origin of time here to the present time, here in the now on Earth. I've plotted here system complexity. I'm going to define that in a very short time. You could synonymously, as I've indicated here, and instead of using the word complexity, if it's too complex, you could say order, which I've already used, information content, which a lot of people use, and I don't think is a good idea, negentropy, which is a negative form of entropy, organization, inhomogeneity. There's a whole bunch of synonyms that can be loosely used for complexity. But the point is, on this graph here that I'm just drawing in a gut feeling, is that over the course of time, and out of the simplicity of the early universe, when the complexity was low, arose some degree of complexity. I don't know whether the universe followed this darker curve, which looks like an exponential curve, or whether it followed this more linear curve, or whether it followed this curve, which is even faster or hyper than exponential. I want to know. I do want to know, using real data. And much of what I've been doing for the last several decades is to try to throw data onto that plot. Among all the systems that I can observe and experiment with and collect data and test, I want to know which one of those curves pertain. There's my definition. Complexity is a state of intricacy, complication, variety, or involvement as in the interconnected parts of a system and its function. We're talking not just in biology about system and function. These other systems also have functions, even inanimately. So here's one such system I just put on here in a general way, just to try to give you a feeling over the next few slides of the differences that I'm talking about when I talk about complex systems, whether they be physical systems, or biological systems, or cultural systems. Here's a physical system, type of system that emerged, we know, in the early universe. It's a star cluster. There's a specific name for which is a globular cluster. It has a name or number, M80. It's the 80th object in the Messier catalog. We know it very well. It hangs around in the halo of the Milky Way. It's very old. That's just why I have it in the early universe here. It formed long ago, about 12 billion years ago. There's a long song and dance about how we can date that. We can maybe raise that later and address that later in the Q&A. But it's a system that has about 1 million stars contained within it, quite unresolved there in the middle, spread over about 100 light years across. But looking at it, it looks relatively simple. I don't need much information to describe that ball. Looks like a beehive. And that's true in general, that physical systems are relatively simple. That's why physicists, when we study some of these things, we Well, I don't completely subscribe to the notion that we should assume all these systems are spherical cows, but sometimes we do, right? Here's another system further up the track somehow, a biological system. Gee, that looks a little more complicated. It looks a little more complex. What is that? That's actually a graphic along the axis of a DNA molecule. It was given to me by a biochemist at Harvard and in the biology department. And I keep looking at the edge here. I was telling somebody the other day, I was in Washington at NASA headquarters, and an astronaut fell off the stage. I mean, if an astronaut can't keep his balance. Anyway, this is along the axis of a DNA molecule. So the scale here is wildly different. This was light years across. This is just nanometers across. And the color code is such that if I remember right, he told me, let's see, blue is nitrogen, green is carbon, red is oxygen, and yellow is phosphorus. Hydrogen is not shown. But the point I'm making as we move toward a representative example of a biological system, that looks a whole lot more complicated than does that. I need, in effect, more information to describe that than I do that. And a cultural system might be something like this, though I sometimes get into trouble showing this. I think it's a perfectly reasonable cultural system. It's the rose window in the cathedral in Paris at Notre Dame. And it's something that we built. Culture built this. I mean, we're part of nature, but nature alone would not have built that without us. And it looks a whole lot more interesting and complex. And indeed, we'll see that many of the systems we associate with cultural evolution do seem to be considerably more complex with regard to this definition. And so we have this kind of, again, superposed on these curves that I'm trying to specify. In a minute, I'm going to give you a data barrage that will show you which one I think is being obeyed, and how I could put on the same page all these systems we're talking about, whether they be physical systems of interest to a physicist generally, biological systems of interest to a biologist, and cultural systems of interest to all of us. What human being have you met who's not interested in a cultural system? Here's another way of viewing that same picture artistically. I'm married to an artist, so it makes it easy. I show a lot of art in my classes at Harvard. In fact, I generally show 3 slides simultaneously at Harvard. The central slide is the slide I work with at the level of the course. The left slide is always a very technical slide for the better student who wants to dig deeper. And the right side is a piece of art for those students who have no clue what I'm talking about. But this is an interesting piece of art because it attempts to capture some of what we've been talking about in the previous slides, where you have the Big Bang universe here, coming out of let's just say a point. More on that later, maybe, or maybe not. And then as the universe expands and cools, it moves out in such a way that we move from physical system to biological system to cultural system. Well, I've got a little carried away here, as you see, in the cultural domain, but the systems are supposed to be becoming increasingly complex in this piece of art that has a considerable amount of artistic license. But it's a general flow. Again, we'll be back to it later, I think, that the universe has moved from an era that was dominated by radiation to one that is dominated now by matter, but one that may be moving toward a universe that's dominated by life. Don't know how many other life forms are out there. So far, despite everything you hear on Fox News and all the rest, we're the only ones. There's no evidence, unambiguously, whatever, for life beyond the Earth. Now, here's a very interesting photograph. I admit I contrived with an astronaut to get this photograph or something like it because I wanted to capture in this one photograph the 3 systems that I'm talking about: physical, biological, and cultural systems. So the physical system is the sun in the background. Could be the Earth too, but it is the sun. That's a very interesting physical object. The biological system is the astronaut. She's joking around with me. She has a little thing. This is her menu. She brought her menu outside the shuttle with her. And she knew I was going to talk about energy flow. She knew I was going to talk about kilocalories in a minute. So she brought out her menu just to, anyway, she's jerking me around. And she's an example of the biological system. And then the shuttle that brought her up there is an example of a cultural system that was built by us technologically. So this one photograph captures the three kinds of systems that I'm interested in, and they all have a common denominator. They all are associated with energy flow. All these systems have through them a certain amount of energy passing through them. The sun certainly has a throughput of energy. Hello? Very obvious. But Kathy is also eating a certain amount of roughly 2,800 kilocalories per day. If she didn't, she'd die. Same with us. And of course, the shuttle needs a certain amount of energy throughput to get it up there. There's a common denominator here in terms of energy. You may suggest other things like information content, et cetera, but I'm hanging my, I guess, reputation on energy. Energy is something I can understand as a physicist. I can define it. I have an intuitive feel for it. I know its units. A lot about energy that I think I have a handle on. Other subjects are a little more slippery. But a physicist would look at a photograph like this in these various systems, and of course would make some assumptions. They'd say, well, all these systems can be considered a box, but not just a box, an open box. And this open box that I've sketched for you at the top tries to suggest what I was just talking about, namely there's a flow of energy through these systems. If the box were closed, there'd be no flow of energy. If there's no flow of energy in the sun, that is, the sun is not fusing, it will shrivel up and it'll collapse. If plants photosynthesizing did not continue to utilize energy coming in through their systems, they would shrivel up and die. And of course, again, if a human being did not take in a certain amount of optimized energy per day, it also would die. All of us would. There's not just a flow of energy, but there's an optimum amount of energy flowing through these systems. So this box, which is open, is shown here, and it's open so that energy, E, can move in, and wastes, Q, can move out. And that's what's happening to all these systems in the same. And then I have entropy there as a symbol S. But this is a way a thermodynamicist, a physicist interested in energy flow, would analyze each one of these systems. You may find it a little odd that, you know, a human would be analyzed in this way, or a space shuttle, a star. Well, I think you can put these things on the same page and analyze these systems in the same way. And that's a means of moving toward unification. And consider this plot here. This was a plot that I drew up inspired from the work by Ilya Prigogine, Nobel laureate in Brussels, now deceased. And he was describing how when some physical systems are energized, they can bifurcate. They can bifurcate in such a way that as a certain amount of energy enters the system can either take advantage of that increased energy and reach some new level of order and complexity, or that system, upon being energized more, can die. This is the dashed line is the rejected states. The solid line, the accepted states. Nature is full of winners and losers. The winners are the ones that continue on by energizing ever so slightly, but optimally, to gain increasingly complex states. We see this all through physics. But of course, the losers take this dashed line. And among biological systems, which I'll address in a moment, more than 99%, it is said by most biologists, more than 99% of all species that have ever lived on the surface of the earth are now extinct. They're losers. It may actually be the case for culture as well. Most societies might also be losers. I'm frankly worried about that a little bit, but that's not the nature of the talk tonight. I just want to compare and contrast this study. I have a star field here from the Spitzer Space Telescope. How many of these stars could be analyzed in this way here, showing how many of those stars, like the sun in the case, the sun continues to build heavier elements contained within it up to a certain level. The sun is building helium now at its core. It will begin to build carbon in about 4 or 5 billion years. And then it will build maybe a little bit of oxygen. But the sun is too small. It will never gain a large enough energy flow contained within it to build elements heavier than that. The sun will then die. in about 5 to 7 billion years, according to best models we have. It will be, after 10 billion years of being a winner, a loser. We won't be around. I wouldn't worry about it. We'll be gone, long gone from another star system if we survive that long. But I want to compare and contrast this way of treating systems that are being changed by their energy inputs with the biological system, which has a very similar story to tell, ever so briefly. This plot now is inspired by the work of Jonas Salk, who was a good friend, the American immunologist who invented the polio vaccine. He described how, for a variety of biological systems, you have systems that are enjoying a stasis or equilibrium with nature, and then they become disturbed by some change in their environment. And some of them can respond and adapt to that change by becoming a more interesting species or a more complex part of the original species. And many others can become extinct. Many others have become extinct. Most of the biological systems, as I just mentioned, become extinct as they are altered in their environments. But you see the similarities between the two kinds of analyses. And I'll throw up a few points here that may be of interest to you. Definition concerning adaptation, a responsive adjustment of a system's structure and function to changes, internal or external, in ways that improve its ability to endure. That's adaptation. All these systems are adapting to these changes. The physicists might say regarding physical systems, rather than adapting, they're adjusting. But it's all part of a generalization of adaptation. And so, selection as well. So definition. Selection is a process whereby those systems that work well survive, and those that don't. The magnificent part of the principle of natural selection, as proposed by Darwin, and stressed by him that it is not likely to be the only principle operating in nature among biological systems, is that the first part of the principle of natural selection does depend on chance. But the second part depends on very definite determinism, non-random elimination. And most such species biologically appear to have been, in fact, non-randomly eliminated. They're losers. Very few systems, the ones I'm seeing out the window now, are the winners thus far. So I'm starting to talk a little bit about life, increasingly more now in this presentation. So I should pause for a minute and ask, what is life? It's really tricky to answer that. I mean, as a physicist, I can go anywhere in the world and ask a similar question, namely, what is matter? And no matter where a physicist is trained, no matter where they live, no matter what their personal persuasion is, every physicist has the same definition of matter, namely anything that has mass and takes up space. But if you have a room full of 100 biologists and you ask them what is life, you're likely to come out of that room with 100 different definitions. There's no common definition among biologists as to what life is. The first year I started teaching in the 70s, I went down the row of Nobel laureates in the biology department, and I just politely knocked on the doors, and I said to these heavyweights, "What's life?" They're studying it. They're biologists. They're studying it. Some of them most of them had operational definitions of life. They talked about reproducibility, functionality, hierarchical structures, etc. Even Jim Watson, who was on the array of Nobel laureates in the corridor there before he left Harvard, spurted out. He says, "Oh, you don't have to define it. I know it when I see it." But of course, that's the Supreme Court's definition of pornography. So that's not a very good definition of life either. So I have developed a definition of life from a thermodynamicist point of view over the years. It constantly changes. It constantly gets revised. It's not cast in stone. And my students tackle me. They'll give this talk next week in Cambridge, and they will intellectually attack me. I know exactly the word they're going to attack me on. But this is an attempt, a long-winded attempt, to present to you my view of what life is, and then show you how I utilize this definition, the first half of which is here, in this presentation of cosmic evolution. Definition: life is an open, got to allow for energy to come in, coherent space-time structure, maintained far from thermodynamic equilibrium by a flow of energy through it, dash, is the second half of this. That's why it's a long-winded definition. And the students originally chuckle, of course, and some colleagues are still chuckling. Dash, a carbon-based system operating in a water-based medium with higher forms of metabolizing oxygen. That's my definition of life. And I'm kind of proud of the fact that I have a definition of life, whereas so many biologists I know, and I'm not denigrating biologists by saying this, it just seems to be the case. They don't necessarily think it's important enough to define life or to come to a common definition of life. Of course, it's a difficult subject to define. It's a lot more difficult than physics. Anything that's living in the backyard is a whole lot more complicated and a whole lot more complex than anything I see in the sky. So it's not only more complex in terms of its composition and its structure and its function, but probably in its operational definition as well. I get a little technical for the people who are technical now. I want to look at some of the data and show you how I utilize these data to try to understand more in a quantitative sense, in an empirical sense, the flow of those curves that were rising, or the gut feeling I have that degree of complexity is rising as you move from physical to biological to cultural systems. Open systems. I can't use just energy alone because, you know, I know darn well that if I compare a galaxy in one hand and an amoeba on the other, there's a whole lot more energy passing through a galaxy than there is passing through an amoeba. But on the other hand, I know darn well just as well that the amoeba in the backyard is more complicated and more complex than is the galaxy. Anything, I say again, that's alive, that's animate, is likely to be more complex than anything that's inanimate or not alive. So I can't use just energy. I want to use energy flow, and I want to normalize it by the bulk of the system. So I normalize it by the mass of the system, and I come up with this term called energy rate density. It's the rate that energy passes through a system of a certain density. It's not a new term. Well, it is a new term in the sense that I'm the one who started using this term in this way. But all sorts of other scientists have used this term and called it something else for decades. Astronomers call this the light-to-mass ratio. Biologists call this the specific metabolic rate. Physicists call it the power density ratio. Engineers call it the power-to-mass ratio. Geologists call it the specific radiant flux. They all have different names for the same term. So I'm trying to develop a term that can be used and a lingo that can be used in a common way among all the sciences, and then explore using this term of energy rate density, how I can quantify, there's the definition, this value passing through all of these different kinds of systems. It's a measure of the amount of energy available to do work or to potentially cause change flowing through a system per unit time and per unit mass. It's really power density if you want to get a little technical about it. And here's some interesting entries into this. I show some generic systems, I show their age, and I show the value of the energy rate density in ergs per second per gram. Erg is a very small unit of energy. Gram is a very small unit of mass. Here's one here. Well, let's see if that works. There it is. Here's the sun, and here's the galaxies. I just run through some math. I won't go through the math. I could do it later if you want to know the details. But for certain objects of certain ages, these galaxies are old. The sun is reasonably old. I'm getting values that are small. That's because they formed long ago, and they're physical systems. Then when I put on, by comparison, in this tabular entry, something that's more akin to life forms, or getting closer to the Earth, in particular plants that photosynthesize, then you see the value as the systems get younger, closer to us in time, have increasing energy rate densities. Photosynthesis is an interesting biochemical reaction, of course, the most common reaction occurring biochemically on the surface of the Earth. It's commonly said that photosynthesis is a highly efficient mechanism that the plants undertake that's not well understood, whereas it's wrong. In reality, if you look into photosynthesis, it's a very inefficient system that is rather well understood. So here's another final entry here. Animals, that's us, humans. I've done it for the case of the human. Here's society, a human aggregate. You notice that as the systems become younger, closer to home along the arrow of time, the values increase. So I could plot this. I could plot those values. I could defend those values as well. But when I plot them, you see a graph that starts looking interestingly like that graph I had at the opening of the talk, where I had complexity plotted here as a function of time on the same scale that was somehow moving up like so. Now I'm doing it with real data. And I'm moving from stars and galaxies up through plants and animals and society and brains. The message here is that when you go through this ton of data, and a data barrage for a wide variety of systems, much greater than I've shown you here tonight, is that you conclude more or less that mature galaxies are more complex than their dwarf predecessors, that red giant stars are more complex than their main sequence counterparts, that animals are more complex, let's say that eukaryotes are more complex than prokaryotes, that plants are more complex than protists, that animals are more complex than plants, that mammals are more complex than reptiles, that brains are more complex than bodies, that society is more complex than individual humans who comprise the society, etc. All that can be shown to be the case quantitatively. Plotting is a little bit more cleanly, and now in a nice linear graph that spreads it out, you can see more clearly this run of complexity as a function of time. It's moving up, and it looks exponential to me. It looks very interesting in the sense that the physical systems have a certain slope here that's moderate. The biological systems have a more peaked slope here, and the cultural systems are really racing up there rapidly in time. The whole thing coming together is approximately exponential. Though I'm hesitating over-interpreting the data and specifying the actual curve. So let me just show you, just very quickly, before I get to some summary slides, a case of an intermediate physical system like the sun. I've shown the sun here in the, with a filter. And I'm talking about something of an intermediate nature on this plot. You can actually plow through. You can actually look into this curve and see how the sun is behaving over the course of time. Even the sun itself, among all stars, also seems to share this movement upward from a newborn star that was relatively simple to the current sun, etc., that becomes increasingly more complex, with a lot of data behind these arguments to bolster them. Here's plants. I'm moving up a little further on the slide just to give you a feeling for how plants would kick in along here in the more recent times. And you can actually work with botanists, as I've done in the herbarium in Cambridge, and show how this degree of complexity for plants that's entering into this master plot up and through here can be shown to also be rising as you move from gymnosperms, angiosperms, C4 plants, which are highly efficient photosynthesizing plants. And finally, you can also examine for animals higher up on the plot, though not quite at the top yet, but among animals that we know and love, like the one you see there, how the systems here among animals, reptiles, mammals, birds, very interesting. It's very interesting, parenthetically, to note that among systems that operate in 3 dimensions, their degree of complexity for their category life forms are increasingly complex. That is to say, among invertebrate, insects that fly are the most complex within that category. Among vertebrae, the most complex systems along this axis here are birds, even in some cases more complex than humans at rest. But when humans are doing something actively, we, thank goodness, exceed the complexity of the bird. But the bird is doing something we can't do. Things that fly, that operate in 3 dimensions, have a magnificent function that we cannot do as humans. So we should not underestimate birds and other things that fly, because their function is magnificent. Wouldn't it be wonderful to fly? And even among machines, where I'm going in a moment, you would see that the machines that fly, like computer-controlled aircraft, they are among the machines, the highest of complex machines that we have been able to build thus far culturally. In fact, I do want to just spend a minute asking what's going on up here? This is degree of complexity as a function of time. I'm not suggesting that we are the culmination as humans or human society of this cosmic evolutionary scenario, but I sure am interested in what's going on up here, because we're up here. Our society, a human society, and the machines we make. Can we analyze that in greater? You can. There's a lot of data that we've accumulated over the course of time. I'll show you what some of it looks like. Society advancing. I'm just looking at the degree of complexity over the last million years or so. And you can see how this value here that I've been plotting, energy rate density, moves up in a reasonable way with some degree of outliers, some degree of exceptions, some degree of data slop, all the sets. There's a general trend from Australopithecines to hunter-gatherers, agriculturalists, industrialists, technologists. And then, of course, you can compare and contrast, which worries a lot of people, the humankind advancing with machines rising. Very interesting plot. They flipped out in Moscow on this one at a meeting where we were talking about AI, extreme, strong AI. And they said, aha, you've done it. You've shown the machines are transcending along the dotted line the advance of humankind. And that may be a solution. Kurzweil was with us, of course. He loved this stuff. That may be a solution or an interpretation of those data, that these curves are crossing way up here at the top of this, that the machines are gaining greater complexity, greater than we can manifest, partly because they have some of that exquisite function, faster than we are. Computers are incredibly fast morons, you might say. I don't know. But to me, I'm not sure I'm buying the notion of this trend. There have been lots of examples in the history of complex systems, history of the universe, where transcendence has occurred without there being any threat. I mean, the issue here is, should we feel threatened by machines because they are becoming more complex and these curves are crossing? But in the history, you know, I talk to archaeologists and biologists and all these other colleagues I have in Cambridge, and they say, well, you know, the birth of language transcended symbolic signaling. Land life transcended sea life at the Cambrian explosion. Life itself transcended matter at the origin of life, early on in the Earth. There are lots of periods of transcendence when you didn't have to necessarily associate them with threat. In fact, I like to think that what these curves are suggesting to us is that there may be these curves may be suggesting what we all feel around us now. I think there's a kind of a mutual coexistence between humans and machines. We are learning from machines, the machines are learning from us, and it's not out of the question that we could begin to develop a symbiosis as an interaction between two different systems in close physical association, humans and machines, usually to the advantage of both, a mutually beneficial relationship. It's a kind of more positive view than feeling negatively threatened or threatened by some oncoming technological singularity that others may interpret this. But those are what the data are showing nonetheless. But I like to think, as I look out into nature, that there are many examples of coexistence. I mean, stars coexist with galaxies. Plants coexist with animals. There are lots of examples where systems have not been totally dominated and destroyed or harmed by other systems that have emerged, but have learned to not coincide, but coexist beneficially. And I'll summarize that major master plot by just showing you this one here that I presented in Washington recently, where I've got the radiation era up here again, early on in the universe, the matter era that we are now populating, the life era into which we may be entering, I'm not sure, plotting this grand, on a single page, complexity as a function of time, all of these many systems moving up along this intriguing. See, what's most intriguing and beneficial and interesting to me, awesome in fact, is that I can put on a single page all of this stuff that I'm talking about, whether it's galaxies, stars, planets, life, society, machines. I'm putting it all on a single page. It's ascent with modification. Big Bang to humankind on the same page, quantified. 10 orders of magnitude in energy rate density, 20 orders of magnitude in spatial dimensions, from amoebas to galaxies, 18 orders of magnitudes in time. I'm able to, as a unifier, as a lumper, to take all this data that I've accumulated and analyze in the same consistent way all of these systems and put the results on one page. Summary. 1. Cosmic evolution is a grand synthesis of natural history. It aims to explain, quantify, and unify the sciences, treating non-equilibrium complex systems consistently and uniformly from Big Bang to humankind. 2. Energy is a common currency in nature. Energy is specific, quantitative metric, energy rate density, generally correlates with system complexity and may drive, at least in part, the process of evolution itself, writ large. Evolution is a universal phenomenon, unceasing, uncaring, and unpredictable. In detail, evolution nonetheless shows general future trends among physical, biological, and cultural systems. And finally, cosmic evolution, I think, is a prime mover. In an expanding universe, energy flows and complexity rises within and among nature's many varied systems, which are islands of order in an otherwise chaotic universe.
Is there a maximum of the complexity in your theory? Physical maximum. What is the possible maximum?
Physical maximum?
Yes. Is the complexity unlimited or not?
I think you're asking, is the flow of energy through some of these systems maximized? I think
if you extrapolate your plot.
Yeah. I don't want to extrapolate the plot because I don't feel confident in extrapolating.
Well,
but that's why I ended this, the penultimate point here, that I think ultimately evolution is unpredictable. Sadly, because we in physics like to hold on to the predictability aspects of systems.
Yes.
But evolution on all scales has an element of chance built into it. And I think that makes, in detail, the evolutionary process uncaring, unceasing, and unpredictable.
Yeah.
So you're not going to get me to extrapolate that plot.
Okay. Okay. So if I don't,
everybody asks the same question.
Okay. So if I don't ask you to extrapolate, then I will ask, what is the maximum allowed complexity?
I don't know the answer to that. I don't know the answer to that. I mean, the same question was asked recently by the leading probably the world's leading paleontologist, Simon Conway Morris in University of Cambridge. He wants to know where that plot's going. He wants to know what the maximum value is. The answer is, I don't know. How can I tell? I just cannot understand how he even thinks I could know that. If there's an unpredictable aspect of it, I don't know how chance is going to affect the outcome of the next series of systems. That one obvious possibility is that it stops, and systems that are enjoying a winner state now of optimal use of energy, including ourselves, would no longer do so. That was an answer. This is the famous Fermi paradox in extraterrestrial intelligence that we debate in around big mahogany tables, for which there's no data and there's no evidence for life elsewhere. But the idea is that the reason there is such eerie silence out there and no evidence whatsoever, any signals or otherwise from extraterrestrial intelligence, is possibly that many of their societies have naturally and automatically and unsurprisingly failed, collapsed. They're losers. Just as most biological systems, 99% or more are failures, losers. It may be in the cultural realm, the natural rule of things, the natural part of cosmic evolutionary scenario, that societies that become sufficiently advanced technologically don't survive very long. Because they can't. The book I'm writing now, I'm entitling it "Use It or Lose," not "Use It or Lose It." Just use it or lose. And the answer, using it, I mean solar energy. We've got to, as a civilization, embrace solar energy and the energy of our parent star, which is not a maximum amount of energy. It's an optimal amount of energy. And those civilizations that do so will survive, and those that don't, probably won't. But I don't want you to pin me down in terms of there being a maximum amount of energy passing through these systems. There is literature out there that suggests that some of these systems that are winners do so because they are maximizing the amount of energy that's passing through them. I don't think it's all about maximum energy. I think it's about optimal energy. These systems have just a little, just the right range of energy flow through them. Too much energy will kill them. Too little energy will starve them. All of these systems survive. All the systems I have on that plot have an optimal flow for their system.
Well, you spoke earlier about
Louder.
you spoke earlier about life, animate and inanimate objects. Don't you think the universe is alive?
Don't I think the universe is alive?
If expanding will eventually cease, I guess.
I think the gentleman is asking whether or not I would claim the universe is alive. That's a big step forward. That's a leap beyond which even I am perhaps willing to say. But this notion that there may be a life era toward which we're moving, where the universe becomes increasingly populated with life forms that are winners and that do survive, could mean that the universe itself will become more populated with life. Whether you can go as far as saying the universe itself per se is alive, that's too much of a stretch for me to handle. Though you may be onto something that I'm not smart enough to figure out yet.
Hi. Yeah, I have a question about the other end of things. Something that I sometimes think I understand, and I read another book, and then it confuses me. And specifically, your books and Brian Greene's books and Fred Spire's books, who of course gets a lot of his stuff from you. And that is what provides, when you have the earlier universe in a state of extreme simplicity, as you talked about, what provides the potential for complexity later on within the second law of thermodynamics?
Yeah, it's the expansion of the universe. The expansion of the universe is creating increasing amounts of free energy. It's free energy is the energy that's available to do work. So actually the quantity that I talked about, energy rate density, is really free energy rate density. So as the universe expands, the universe increasingly produces more of that free energy that's available to go to work, to produce change, and to build systems. That's my take on it. And I discussed that a lot in a Harvard University Press book that I wrote in the year 2000. Don't buy it, it's unavailable in libraries. Although all copies of it have been stolen out of the Harvard libraries, which worried me originally, and then Freeman Dyson mentioned to me at Princeton, he said, that's a very good sign. When your book is repeatedly stolen, it's in great demand. I don't know. But I think it's just the expansion of the universe. And I could get into more technical details with you if you like. I could even pull up another slide, but I think it would get too technical for the variety of people here. Maybe we can talk about it a little bit later. But Fred does talk a little bit about that in his book as well, as he talks about a lot of the stuff that yeah. Joanne, are you directing? Okay. I see somebody there in the darkness. Yep, go ahead.
Is this on?
Yep.
Yeah, okay. I really enjoyed putting everything into this beautiful theory. But you left one thing out, and I want to ask you about that.
Go ahead.
Consciousness?
Yeah. To me, that's a good one. I thought it was going to be something else. Oh, this is interesting. Consciousness, I was on live PBS once introducing two people. I guess I'll say who they were. One was Roger Penrose next to me from Oxford, and the other was Dan Dennett from Tufts. And they had just written 900-page tomes on the brain and consciousness. And as I introduced them, I said something like, why is it that leading scholars in brain theory write books that are kind of indirectly proportional in size to the amount of stuff they actually know? This came out live on PBS. So needless to say, those guys won't talk to me anymore. But But it is amazing that so many of the books that you're probably referring to, whether written by Dan Dennett, or it was a good friend actually, and Roger Penrose and so many others, go on and on and on. And yet, to me, I haven't written a book about consciousness, but to me, consciousness is just what the brain does. The brain, like all of these systems, has a structure and a function. Sometimes the structure is more dramatically indicative of complexity, as in physical systems. Other times, function is more dramatically appropriate, as with, I imagine, birds that are flying. It's a magnificent function they have. But both are contributing. But the brain, too, has structure and function. And to me, the meat of the brain is just the structure. And what the brain does in terms of function is just consciousness. I'm not sure if it's anything more than that. So I could write that in one page rather than 900 pages. But I'm not an expert, so maybe I'm missing the other 899 pages. Your question is a good one. It comes up all the time. A student this term will be writing a paper, I'm sure it'll be a very good one, in my class on moral consciousness. He thinks there's a potential for the next leap forward beyond a life era, radiation era, matter era, life era would be the era of moral consciousness. I'm not sure what he's talking about, but I'm looking forward to reading his paper. Good question. I just don't know how to handle it any better than that.
So we start the rise in complexity at the beginning of the universe, right, where there's no complexity, basically. In the far future, though, maybe 1 trillion years or more,
You're pushing beyond my plot, but go ahead.
I know, but we have this thought that the universe would end in like a big freeze.
But what?
Right. That we have this thought the universe might end in ever expanding, right, as ever expanding. So it would be at a big freeze where stars go out and
It's Robert Frost. Will it end in ice or will it end in fire?
right.
I think it's going to end in ice.
But that would be a state of less complexity than the present, right? So
What we haven't talked about this evening is the accelerating universe. Not only is the universe expanding, but it appears to be accelerating. Its expansion is moving out faster and faster, and that leads to the great missing link in physics today, which is dark energy, not just dark matter, but dark energy. That's pushing the universe out at faster and faster clips, suggesting that we are moving toward an epoch in the future at some point when, all the complexity is potentially broken down and the universe is achieved in a state of maximum entropy. I mean, in the end, the second law of thermodynamics will win, even despite gravity. Despite the relentless pull of gravity, the second law will prevail. I'm convinced of that. And in the end, everything will be in a uniform equilibrium state when all the complexity will have broken down. But that's so far in the potential future that it doesn't even really interest me, because I can't do anything with it in my quantitative world. But people write whole papers about that, and whole review papers, and even books. But the far, far future is just something I'm very reluctant to speculate about, because I think once I start unduly speculating, I will diminish the importance of this work here. I want to limit the speculation, because there are enough problems addressing the outliers and the exceptions and the issues that are coming my way by way of intellectual attack on these issues, without opening myself up nakedly to speculation about the far future. I'm just not going to do that. You can do it if you like, though. But I think ultimately the bottom line is the second law will win, and the complexity will crash everywhere. But it's so far in the future, it's not of interest to me.
Hello. Anyway, the question is a two-part question. The first one is, would it be okay to conclude from your presentation that the
Start again. Would it be what?
Would it be okay to conclude from your presentation that the proper definition of complexity would be this quantity that you have introduced as the free energy rate flow? Well, what is the proper definition of complexity in your theory?
I gave you my definition of complexity in words, and then I developed this energy rate density as a proxy, at least, as a metric for complexity. Very few people who work in complexity science have an actual quantitative metric.
Yeah.
I'm trying to develop that metric.
So the proper definition of complexity of the system would be that quantity that you define. Then.
I think that's my hypothesis.
Okay.
That's what I'm trying to test.
So I wanted to make sure I didn't misunderstand you there. The second one has to do with, okay, you don't want to extrapolate.
Yep.
And then you talked about laws earlier.
I talk about what?
Laws, possible laws, that science is characterized by invariance, by laws, and
Yes.
so forth. And so laws, to some extent, stick their neck out on some prediction. Ultimately, the way you use laws is to make predictions of some sort. So if you don't want to extrapolate and you don't want to posit any laws, then the question becomes, what is the usefulness or the utility of the theory?
Explanation, description. I want to explain as best I can what I see out the window now. I want to understand and be able to describe, whether it be to a doctoral seminar or to a bunch of US senators, I want to be able to explain how humanity fits into what's present now in the universe. I'm not that interested necessarily in using this information to extrapolate where we may be going, because I don't feel confident to be able to do that. And I want to stay with some degree, maybe it's of humility, within the bounds of what I think is reasonable. But I think it is reasonable to suggest that these data and this analysis may be on the road to a discovery of a set of universal laws, that's a strong word, principles or mechanisms that apply to all such systems that we see out in the universe now.
So you're saying that laws are possible, but we can envision them now, but you're not exclude them entirely as a possible conclusion or consequence of the course you have plotted here.
No, I'm not excluding any of that.
Okay.
I'm just not smart enough to figure out how to go beyond that curve. I'm not sure if it's safe
Because
and reasonable.
Otherwise, it sounds like Monday morning quarterbacking. Kind
More than what?
Monday morning quarterbacking.
Monday morning quarterbacking.
You know the expression there.
Yeah, I do. Yeah, Brady's my quarterback, right?
Yeah, I understand.
But the point is, I'm trying to put quantitative analysis to bear on this. I'm trying to go beyond just words. I'm trying to go beyond what Monday morning quarterbacking implies. And I'm not being defensive here. I am trying to, in a cautious way, with caveats all over the place, trying to develop a metric in such a way that applies uniformly, consistently, and coherently to everything I see out the window now. But I don't want you to force me, I'm not going to allow you to force me to extrapolate this on into the future, or to extrapolate it to systems that might emerge later on. I just don't know how to do that. I don't know if anybody would be able to even conceivably do that, given that chance plays a role along with determinism. It's chance and necessity. Read Jacques Monod. Hasard la nécessité. A great book written in the 60s. Admittedly, he wrote it in existentialist French. He was worried about chance being on. You know, none of these systems are informed by chance and chance alone. So there's got to be an element of chance and determinism as well. So we can characterize both these things, but because chance is an integral element of how these systems change, I don't see how you can ever predict in detail. That's what it says here, predict in detail. I can predict in general. I can talk about general trends. And that's what I tried to do with regard to that very controversial plot where I've got those curves of machine crossing humankind that excite the AI people, the artificial intelligence people, and worry other people that machines are going to threaten us. Whereas I keep saying, you know, I think it's just a mutual symbiosis between us and machines, and it's happening every day around us now. We find machines interesting. They're useful to us. I mean, just think of the machines that are around you in your daily life. Just think. And we're using them in a mutually beneficial way. They are also learning from us. I don't think there's anything to fear from that.
Well, thank you. At the risk of being a little dense.
Who's speaking?
I am. Okay, yeah.
Go ahead.
Can you try to explain energy rate density a little more, a little differently? I didn't quite get it. And
Sure.
everything is
Sure.
central to that in your...
Yeah.
Okay, thank you.
Here's a box. Maybe the box is representing a galaxy or a star or you or a society or a machine. And there's a certain amount of energy flowing through that system. If that system has a certain amount of mass, bulk. So I can measure the degree to which, the rate of which energy flows through that system per unit mass. For example, you eat about 2,800 kilocalories per day. You do it per day. You have a certain mass. I bet you're about 70 kilograms. 77 kilograms. And so I can just take the amount of energy flowing through your body, 2,800 kilocalories per day, divided by the mass of your body. And I've got the energy rate density flowing through your body. The answer is about 2 by 10 to the 4 ergs per second per gram. It's just a measure of the rate at which energy is flowing through a system of mass. But I've elected to normalize it by the bulk of the system. Because I know I can't be using just, I want to hang my hat on energy, but I know it can't be energy alone. Because again, a galaxy has so much more energy than an amoeba. Yet I know an amoeba is more complex than a galaxy. So you can kind of say, well, he's fudging it. But lots and lots of people normalize in physics and in other communities by the bulk mass of a system, in order to be able to fairly and squarely put all of those systems in an equal way on the same page. That's my ultimate objective, to analyze all of these systems in the same consistent, uniform way. I'm a lumper tonight. I'm a splitter tomorrow. Because the work of the splitters goes into this work. Then somebody has to. I mean, E.O. Wilson's a good friend. You probably know E.O. Wilson, the father of sociobiology. He's 87 now, a wonderful guy. And he's a synthesizer. And he likes to say he's not smart enough to be a specialist, to be a splitter. He's only good at lumping. But of course, that's what he's famous for. That's what he's so renowned for. And he likes to say that at any given time in history, there's only a few people who are synthesizing. We have the impression going back in time that, you know, Da Vinci and Galileo and Newton and Darwin, they were all sitting around the table talking to one another. They were never alive at the same time. None of them. Even Galileo died the year Newton was born. They never even lived at the same times. So they were all individual mavericks. I'm not trying to compare myself to these people. I'm just saying that every once in a while, people come along like E.O. Wilson to synthesize aspects. And that's what I aspire to do as well. And that's selfishly because with my left hand, I want to know before I leave this planet who I am. This is my way of doing it. I could have been an artist. I could have been a musician. Well, badly. But I elected science because somehow I was drawn to the notion that, yeah, there ought to be a way to test an idea, to test a belief, to be a little more skeptical about something. And that's what I try to ingrain in my students, to always to be skeptical about what I'm saying. Of course, it backfires because my classes are just intellectual attacks. You know, I arrange the 50 students in a great big U-shaped well, and then I operate in the middle of the well. And they're kind of, the crossfire is coming from all angles about, you know, what you just said, define that, what the hell are you talking about? It's fabulous. but it keeps me on my toes. Is that a little bit better understanding of energy rate density?
It did. I'm still
Sounds-
not sure how it connects to this, but I need to think about it.
Think about
it. How does it relate to a society, for example, or a bird, for example?
Well,
One
I just
seems
gave
complex,
you,
one
I just
seems-
gave you your energy rate density for your body. I can do the same thing for a bird. I know what a bird eats. I know what the mass of the bird is.
But how does it relate to
So-
the evolution, to something that is higher order or moving to a new direction or doing something new? How does the energy rate density relate to that growth or that?
All these systems are affected by the environment, and they utilize energy flowing through them optimally. If the energy flowing through them upon change by the environment is outside of the optimal range, evolution will select them out. They will be selected out. That's why most systems are losers. The energy flowing through them is too great, blows them up. Or energy flowing through them is too little, they're starved. Most systems fail because when they change, when the environment changes, the energy flowing through those systems is not within the optimal range. That's what I'm also trying to find and specify what the optimal ranges are for galaxies, stars, planets, humans, society, machines.
So are you saying the more optimal they become, the higher order they become?
No, I don't want to do that. I didn't say that. I'm just saying within every category of system that has a certain amount of complexity, there's a certain range of optimality associated with that. So it's not the same as saying the more, no, it's not the same as, we're going to have to talk about more of that.
One more. So what's the driver of expansion, the higher order?
While the expansion of the universe, I think, is the driver of this whole story, you're asking more fundamentally, what is the driver of the expansion?
Cosmic expansion, as you say.
Yeah. Well, if I knew the answer to that, I'd be famous. I mean, that's like asking not what is the origin of the universe, what is the origin of the origin? That's a hard question. Even I'm not prepared to answer that. I don't know. I tell my students, and I stressed last night, though, repeatedly, that we do not want to view the universe as a big bang that exploded. There's no explosion there, which then sent the galaxies traveling out into already existing space. Because Einstein taught us that at the moment of the beginning of the universe, at the Big Bang, the universe simply began to expand. And the fabric of space-time, space and time, expanded out, and the galaxies are along for the ride as parts of that fabric. Galaxies are not traveling through space per se. But what drove that expansion, I don't know. That's another talk. That'll be next week's talk in Cambridge.